somewhere out there, far beyond our own quiet sun, there are worlds where the sky holds not one star, but two. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. Picture a planet orbiting two suns at once. In the morning, one star rises in the east, golden and warm. Hours later, a second star climbs above the horizon, smaller and cooler, casting long blue shadows across the ground. Two sunsets, two dawns, a sky that never quite looks the same twice. This isn't science fiction. It's the reality for a huge portion of the universe. More than half of all the stars you can see on a clear night are not alone. They travel in pairs, bound together by gravity, circling each other across distances that stretch the imagination. Some pairs are close enough that their outer layers brush and blend. Others are so far apart that one full orbit takes millions of years. But they are always connected, always pulling, always dancing around a shared center point that neither one ever reaches. We call these systems binary stars. Binary simply means two. Two stars born together or captured by each other's gravity, locked in a permanent gravitational embrace. Our own sun is actually unusual. It travels alone through the galaxy, with no stellar companion. Most stars in the Milky Way are not like our sun in this way. Astronomers estimate that somewhere between 40 and 80% of all stars in our galaxy exist in pairs or even larger groups. The exact number is still being refined as telescopes improve, but the pattern is clear. Solitary stars like our sun may actually be the exception, not the rule. Think about what that means for the night sky. When you look up at a star and see a single point of light, there's a good chance you're actually looking at two stars so close together that your eye blends them into one. The light from both stars travels across light years of empty space and arrives at your eye as a single soft glow. Two suns hidden inside one tiny spark of light. The star Albireo, which sits at the head of the constellation Cygnus the Swan, is a beautiful example of this. Through even a small telescope, Albireo splits into two distinct stars. One glows a deep amber gold, other shines a cooler, softer blue. They orbit each other very slowly, taking perhaps 100,000 years to complete a single loop. Side by side in the eyepiece, they look like a jewel set in black velvet. The universe seems to prefer company. There's something deeply calming about that idea. Gravity, the same quiet force that holds you to the ground right now, reaches across trillions of miles of empty space and keeps two stars in step with each other. No engine, no effort, just the gentle, patient pull of mass on mass, holding the pair together across billions of years. Binary stars come in every combination you can imagine. Two stars roughly the same size and color, circling each other like equal partners. Or one enormous star paired with a tiny dim companion, the small one tugged along in a wide, sweeping arc. Some pairs include stars that are still young and forming. Others include stars that have already died, collapsed into dense, white-hot embers called white dwarfs, still orbiting a living companion long after their own fires went out. Each combination tells a different story. Each pair is a small system unto itself, with its own rhythms, its own timescales, its own fate. And yet, all of them follow the same rules. The same physics that governs a stone falling from your hand also governs two stars 1,000 light years away. Gravity doesn't change. Distance doesn't weaken the elegance of the math. The universe runs on the same handful of laws everywhere you look, and binary stars are one of the clearest, most beautiful examples of those laws at work. We are going to spend this whole episode inside that world. We'll look at how binary stars are born, how they age, how they sometimes steal material from each other, and how they die. We'll look at the strange and violent things that can happen when one star in a pair runs out of fuel while the other keeps burning. But for now, just hold this image. Two suns, one sky, a planet bathed in double light, shadows falling in two directions at once. Somewhere in this galaxy, that world exists, and the stars above it have been circling each other since before our own sun was born. Stars are not born alone. That might surprise you. We think of stars as solitary things, single bright points scattered across a dark sky. But But most stars come into the universe with a companion. They form together from the same cloud of gas and dust, and they stay bound to each other for billions of years. It begins with a nebula. A nebula is a vast cloud of hydrogen gas and dust floating in space. These clouds are enormous. Some stretch across hundreds of light years. A single light year is about 6 trillion miles. These clouds are so wide that even light, moving at 186,000 miles per second, takes years to cross them. Over time, gravity pulls parts of a nebula inward. The gas starts to clump together. As it clumps, it spins. And as it spins faster, something interesting happens. The cloud doesn't always collapse into one single point. Sometimes it breaks apart into 2 separate clumps, spinning around each other. Each clump keeps pulling in more gas. Each one grows hotter and denser at its center. Eventually, the pressure at the core gets so intense that hydrogen atoms begin to fuse together. That fusion releases enormous energy. The clump ignites. A star is born. And because 2 clumps formed side by side, 2 stars are born, a binary pair. Scientists call this process fragmentation. The original cloud fragments, or splits, into pieces during collapse. The conditions that cause fragmentation are still being studied, but researchers believe the rotation speed of the cloud plays a big role. A cloud that spins too fast can't hold itself together as one piece. It tears into 2, or sometimes more. This is why binary stars are so common. The conditions that make fragmentation happen are not rare at all. They're ordinary. Both stars in a binary system form from the same original cloud. That means they share the same basic ingredients. They're made of the same mix of hydrogen, helium, and trace amounts of heavier elements. They're roughly the same age. Think of them like twins, not identical, but born from the same source at nearly the same moment in cosmic time. The 2 stars are not always the same size, though. Even small differences in how much gas each clump gathered can lead to very different stars. One star might end up with twice the mass of its companion. Mass, the amount of material packed into a star, controls almost everything about how a star lives and dies. A more massive star burns hotter and brighter. It also burns through its fuel much faster. So two stars born at the same time from the same cloud can age at very different rates. One might still be glowing steadily, while its companion has already swelled into a giant. The distance between the two stars at birth varies enormously. Some binary pairs form very close together, close enough that you could fit only a few of our suns between them. Others form so far apart that they're separated by distances measured in light years. The distance between them shapes everything about how they'll interact over the billions of years ahead. Our own sun has a diameter of about 865,000 miles. Imagine lining up nearly 900,000 Earths side by side. That's how wide our sun is. Now imagine two objects that size, or larger, orbiting each other across a gap of millions, or even billions of miles. The scale is hard to hold in your mind, but the universe has plenty of room for it. The age of most binary systems is measured in billions of years. Our sun is about 4.6 billion years old. Many binary pairs are older than that. Some formed in the early universe, more than 10 billion years ago, when the first generations of stars were just beginning to light up the darkness. Those ancient pairs are still out there, still orbiting, still bound together by gravity across unimaginable stretches of time. What holds them together is simple. Gravity, the same force that keeps your feet on the ground, that keeps the moon circling Earth, that keeps Earth circling the sun. That same quiet, patient force keeps two stars locked in orbit around each other. Neither one flies away. Neither one falls inward. They find a balance, and they keep it year after year, century after century, for billions of years. That balance is not fragile. It's steady. It's the kind of steadiness that only comes from forces working in perfect proportion to each other. Two stars born from the same cloud, holding each other in place across the dark. That is where this story begins. Every binary star system begins the same way. A vast cloud of gas and dust, drifting cold and dark through space, starts to collapse under its own weight. Gravity pulls the cloud inward. The cloud spins faster as it shrinks, the same way a skater pulls her arms in and speeds up. That spinning motion is the key to everything that follows. As the cloud collapses, it doesn't always form one neat center. Sometimes the cloud is slightly uneven. One side is a little denser than the other, or the cloud is simply too large and too fast to settle into a single point. When that happens, the cloud breaks apart into two separate clumps. Each clump pulls in more gas and dust. Each one heats up at its core, and slowly, over hundreds of thousands of years, two stars ignite side by side. This is the most common way binary stars are born. Scientists call it fragmentation, which just means the original cloud broke into pieces before it could form one star alone. The two stars that come from this process are almost always similar in age because they formed from the same cloud at roughly the same time. They share a history that stretches back to before either of them existed. There is a second way binary systems can form, though it's rarer. Two stars that formed separately can drift close enough together that gravity locks them into orbit around each other. This kind of pairing is more likely in dense star clusters, where hundreds or thousands of stars are packed into a relatively small region of space. In those crowded places, close encounters happen often. Gravity does the rest. Once two stars are bound together by gravity, they begin their orbit. They don't orbit each other the way you might picture, with one star sitting still while the other circles around it. Both stars move. They orbit a shared point between them called the center of mass, or the barycenter. If the two stars are equal in mass, that point sits exactly halfway between them. If one star is heavier, the center of mass shifts toward the heavier one. Either way, both stars are always in motion, always circling that invisible point together. The shape of their orbit matters too. Some binary pairs move in nearly perfect circles, tracing smooth, steady paths through space. Others follow long, stretched-out ellipses, swinging close together, and then pulling far apart before coming close again. The shape of the orbit depends on how the system formed and how much energy was present when the two stars first settled into their gravitational bond. The time it takes for one full orbit varies enormously from one binary system to the next. Some pairs orbit each other in just hours. They are so close together that they race around their shared center of mass faster than Earth completes a single day. Other pairs are separated by enormous distances, and their orbits take thousands of years to complete. There are binary systems where the two stars are so far apart that astronomers can only confirm they're connected by tracking their slow, shared motion through the galaxy over decades of careful observation. What keeps them locked together is the same force that holds you to the ground and keeps the moon circling Earth. Gravity doesn't care about the scale. It works the same way, whether it's holding a pebble to a hillside or binding two suns across 1 trillion kilometers of empty space. And here is something quietly wonderful about that. The two stars in a binary system never actually touch each other's gravity like a hand reaching across a table. The force between them weakens with distance, following a precise mathematical rule. The farther apart they are, the weaker the pull. But as long as neither star gains enough energy to break free, they stay bound. They keep dancing. They have been dancing, in many cases, for billions of years. The cloud that made them is long gone. It burned away or scattered into space as the stars ignited. But the motion that cloud carried, that original spin and momentum from the very first collapse, is still alive in the orbit. The two stars carry it forward, turning slowly or quickly depending on their distance, tracing paths that were set in motion before the solar system existed. There is something deeply calming about that idea. Two stars, born from the same cold cloud, held together by the same quiet force that shapes everything in the universe. They have never stopped moving. They have never drifted apart. They simply keep going, circling that shared invisible point, the way they always have, the way they always will. Most of the universe is made of just two things: hydrogen and helium. These two gases were born in the first few minutes after the Big Bang, when the universe was still a hot, bright, roaring place. Everything else, every heavier element, every grain of metal, every atom of oxygen in your lungs came later. It came from stars. Binary stars are part of that story. and the materials inside them connect directly to everything around you. A star is mostly hydrogen. That hydrogen sits at the core, packed so tightly that atoms fuse together under enormous heat and pressure. When hydrogen atoms fuse, they form helium, and in that fusion, a tiny amount of mass converts into energy. That energy is light and heat. That energy is the sun's glow. In a binary system, two stars are doing this at once, each one burning through its hydrogen supply at its own pace, each one shining with its own steady light. But hydrogen doesn't last forever. When a star begins to run low, it starts fusing helium instead. Helium fusion creates carbon and oxygen. These are heavier elements, built one layer at a time inside the star's core, like rings inside a tree. The more massive the star, the deeper the fusion goes. A very massive star can fuse carbon into neon, neon into silicon, silicon into iron. Each step builds something heavier than the last. Iron is where the process stops. A star cannot fuse iron to release energy. Iron absorbs energy instead of releasing it. When an iron core builds up inside a massive star, the star has reached the end of a long road. What happens next? The collapse, the explosion, the scattering, sends all those elements out into space. Carbon, oxygen, silicon, iron, all of it flung outward into the dark. Those scattered elements become the raw material for everything that comes after. They drift through space as clouds of gas and dust. Over millions of years, gravity pulls those clouds together. New stars form, and around those new stars, planets can form too, built from the same elements the old stars made. The iron in Earth's core was forged inside a star that died long before our sun was born. The calcium in your bones was made in a stellar core. The oxygen you breathe was fused inside a star and scattered by its death. You are, in a very real sense, made of ancient starlight. Binary stars play a special role in this process. Because they come in pairs, they interact with each other in ways a single star never could. And those interactions can change what elements get made and how those elements get released. A binary system is not just two stars burning side by side. It's a partnership that that shapes the chemistry of the space around it. Both stars in a binary system formed from the same original cloud of gas and dust. Scientists call this the natal cloud, the birth cloud. That means both stars share a similar starting chemistry. They were built from the same ingredients, but because they often differ in size, they burn through those ingredients at different rates. The more massive star lives fast and dies young. The smaller star burns slowly and quietly for billions of years. When the larger star eventually dies and scatters its material outward, some of that material can fall toward its companion. The smaller star can actually absorb some of the elements its partner spent its whole life making. In this way, a binary system passes chemistry from one star to the other. It's a kind of slow, cosmic inheritance. Helium, carbon, nitrogen, oxygen. These are the four most common elements in the universe after hydrogen. Scientists call them the building blocks of organic chemistry, the chemistry of living things. Every one of them was forged in a stellar core. Every one of them has traveled through space, through clouds, through the formation of new solar systems, to end up here. When you look at a binary star system, you're looking at two furnaces running at once. Two cores fusing hydrogen into heavier elements. Two stars building the raw material that the universe will use again someday. Nothing is wasted. Nothing is lost. The elements made inside a star today will drift through space for millions of years and then find their way into something new. A planet, an ocean, a living cell. The universe recycles everything. Stars are where that recycling begins. And binary stars, with their paired cores and their long shared lives, are some of the most productive forges in the galaxy. Some stars hide. You cannot see them with your eyes, or even with a telescope pointed at the right patch of sky. They sit in the dark, tucked behind distance and silence. But they cannot hide from the forces they create. Gravity always leaves a trace, and scientists have learned to read those traces like a language. The most powerful tool for finding invisible stars is something called the Doppler effect. It works the same way a passing train changes its sound as it moves toward you and then away. When a star moves toward us, its light gets compressed into slightly bluer colors. When it moves away, that light stretches out into slightly redder ones. This tiny shift in color tells astronomers which direction a star is moving and how fast. Now imagine a binary system where one star is bright and the other is too dim to see. As the bright star orbits its hidden partner, it moves toward us for part of its orbit, then swings away. Astronomers watch the color of its light shift back and forth in a steady rhythm. That rhythm reveals the hidden star as clearly as a shadow reveals the shape of something standing in the sun. Scientists call this method radial velocity detection, meaning they measure the speed of a star moving toward or away from us along our line of sight. The shifting light doesn't just confirm that a second star exists. It also tells scientists how long the orbit takes, how wide the orbit is, and even the minimum mass of the unseen companion. Mass is the amount of matter packed into an object. The heavier the hidden star, the harder it tugs on its visible partner, and the stronger the color shift becomes. From a single ribbon of light, scientists can reconstruct the shape of an entire invisible dance. Some binary systems reveal themselves in a completely different way. When two stars orbit each other in a plane that happens to line up with our view from Earth, one star periodically passes in front of the other. When that happens, the total brightness of the system dips. It dims slightly, then recovers, then dims again on a perfectly regular schedule. Astronomers call these eclipsing binaries. The word eclipse here means exactly what it does when the moon slides in front of the sun. One object blocks the light of another. The dimming pattern carries enormous detail. If the two stars are different sizes, the depth of the dip changes depending on which one is in front. A large, dim star crossing in front of a small, bright one creates a different signature than the reverse. By studying the shape of the dip, its depth, and its timing, scientists can calculate the sizes of both stars, the tilt of their orbit, and the distance between them. All of this from a light curve, which is just a simple graph of brightness over time. There is something quietly astonishing about this. A scientist sitting at a desk on Earth, studying a graph of flickering light, can describe two stars millions of trillions of miles away. She can tell you how big they are, how fast they move, how close they orbit. The universe keeps no secrets from those who know how to listen. Astronomy offers a third method. This technique tracks the precise position of a star against the fixed background of far more distant stars. A single star should hold a steady path across the sky over years and decades. But a star with an unseen companion wobbles. Gravity from the hidden partner tugs it slightly off course, first one way, then the other, as the orbit progresses. The wobble is tiny. We're talking about shifts smaller than the width of a coin seen from across a city. But modern instruments can detect them. Each of these methods works because gravity cannot be switched off or hidden. It acts across empty space, across vast distances, without pause. A star cannot orbit another star without advertising that fact to anyone patient enough to look. The pull between them shapes their motion, and their motion shapes their light, and their light carries the whole story across the cosmos to us. What makes this feel so remarkable is the scale of the indirection involved. We are not seeing these stars directly. We are reading the fingerprints they leave on light. We are inferring whole worlds from the gentlest of signals. And yet, the picture that emerges is precise and real. Two stars circling each other in the dark, billions of miles from here, known to us completely because the universe follows rules, and those rules leave evidence, and we have learned slowly and carefully how to find it. Gravity is quiet. You can't see it. You can't hear it. But in a binary star system, gravity is everything. It's the invisible thread that holds two suns together across distances so vast they're almost impossible to picture. Let's try to picture them anyway. Some binary pairs orbit each other at a distance smaller than the distance between Earth and our Sun. That gap from Earth to our Sun is about 93 million miles. It takes light 8 full minutes to cross it. And yet, some binary stars are even closer than that to each other. Two enormous, blazing suns, separated by less than the distance we travel around our own star every year. When you think about the sheer size of a star, that closeness feels almost reckless. Our sun is so wide that about 109 Earths could line up side by side across its face. Now imagine two objects that large, sitting closer to each other than Earth sits to its own star. The gravity between them would be immense. Their surfaces would be pulled and stretched by each other's tug. The space between them would be filled with radiation, with heat, with light so intense that no planet nearby could hold liquid water on its surface. Life, as we know it, would have no quiet place to begin. And yet the universe makes these close pairs all the time. At the other end of the scale, some binary stars are separated by distances that make the mind go soft trying to hold them. Certain wide binary pairs orbit each other at distances measured in light years. A light year is about 5.88 trillion miles. These stars move so slowly around each other that a single orbit can take millions of years to complete. They are bound together by gravity, technically a pair, and yet they sit so far apart that from one star, the other would look like nothing more than a very bright point of light in the sky. A companion star, barely distinguishable from the background stars around it. The gravity holding those wide pairs together is incredibly weak by cosmic standards. A passing star, or even the slow gravitational pull of the galaxy itself, can eventually tug them apart. Scientists call this kind of disruption a soft encounter. The pair doesn't explode or collide. One star simply drifts away, very slowly, over millions of years, until the bond between them is gone. Two stars that were born together, that spent billions of years in each other's company, quietly parting ways. That slowness is part of what makes space so hard to truly feel. Everything happens on timescales that dwarf human experience. Now, think about the gravity between close binary stars. In tight pairs, the gravitational pull each star exerts on the other is strong enough to change the shape of the stars themselves. Stars are not perfect spheres when they're close to a massive neighbor. Gravity stretches them. A close binary star can become slightly egg-shaped, bulging toward its companion the way Earth's oceans bulge toward the moon during high tide. This effect is called tidal distortion, the same basic force that pulls our oceans back and forth. just operating on a scale billions of times larger. The moon's gravity moves entire oceans. A companion star's gravity can deform the body of a sun. There's a special boundary in binary systems called the Roch lobe. This is the region around each star where that star's gravity is dominant. Picture two soap bubbles pressed together, each one holding its own space. As long as a star stays within its own Roch lobe, it keeps its material to itself. But if a star swells up and grows beyond that boundary, its outer layers spill across toward its companion. Gravity takes over, and matter begins to flow from one star to the other. This is one of the most dramatic things that can happen in a binary system, and it all starts with a simple question of scale. How big is each star, and how close are they sitting to each other? The numbers that govern binary stars are the same numbers that govern everything. The same gravity that holds you to the ground, that keeps the moon in its path, that pulls the tides across the ocean floor, is the same force stretching distant suns into egg shapes and slowly drawing stellar material across the void between two stars. The scale changes. The force does not. Gravity doesn't care how big or small the object is. It just pulls, quietly, patiently, across whatever distance separates two masses. In a binary system, that pull never stops. Not for a single second. Not across millions of years. Two stars locked together, falling toward each other forever, and forever missing. Some binary stars are so far apart that light itself takes years to travel between them. Others are so close that their outer layers brush and blend together. Between those two extremes lies a whole spectrum of pairings, each one beautiful in its own way. Each one following the same simple rules of gravity and light. The widest binary pairs are called visual binaries. That name comes from the fact that we can actually see both stars as separate points of light through a telescope. They look like two glowing embers set side by side in the dark. The space between them can be enormous, sometimes hundreds or even thousands of times the distance between Earth and our sun. At those distances, the two stars barely seem to notice each other. They drift in slow, wide circles, taking thousands of years to complete a single orbit. Imagine floating in the space between them. You would see two suns hanging in the black sky, each one a different color, each one burning at its own temperature. If one star is older and cooler, it might glow a deep amber or a soft orange red. If the other is younger and hotter, it could blaze in pale blue-white. The contrast between them is stunning. The sky around you would not be fully dark. It would carry a faint, warm glow from two directions at once. These wide pairs move so slowly that early astronomers sometimes watched them for decades without seeing any change at all. The German-British astronomer William Herschel was one of the first to confirm that these pairs were true gravitational partners, and not just stars that happened to line up in our line of sight. He watched several pairs over many years and noticed the slow, steady curve of their motion. That was a turning point in how we understood the sky. Tight binary pairs are a different world entirely. These are called close binaries, and the distance between their two stars can be smaller than the distance between the Sun and the planet Mercury. At those ranges, the stars pull on each other with enormous force. Their shapes change. Gravity stretches them slightly toward each other, so instead of being perfect spheres, they bulge at the sides facing their partner. They look less like two round balls and more like two eggs pointed toward each other, their surfaces swelling in the direction of the pull. If you could hover above one of these close pairs, the view would be unlike anything in our own solar system. The companion star would fill a huge portion of the sky. It would not look like a distant point of light, the way our sun looks from Earth. It would look like a wall of fire, a curved, glowing surface stretching wide across your field of view. The heat coming off it would be immense. The light would be blinding. The surface of the star beneath you would be churning with bright plasma, sending arcs of hot gas looping upward like enormous flames. The color of that surface depends on the star's temperature. Cooler stars glow red or orange, like the color of a coal just before it goes dark. Hotter stars burn white or blue-white, like the center of a flame. In a close binary where the two stars are very different temperatures, the contrast is sharp and vivid. One side of the sky blazes cool red, the other blazes hot blue. The space between them shimmers with radiation. Some close binaries are so tight that their orbital periods, the time it takes them to complete one full orbit around each other, are measured in hours rather than years. There are binary pairs that circle each other in less than a single Earth day. Their surfaces race past each other at tremendous speeds. The tidal forces between them, the stretching and pulling caused by each star's gravity, create constant motion on their surfaces. Hot gas swirls. Bright spots flare and fade. Wide pairs and close pairs are not separate categories with a hard line between them. They sit at opposite ends of a long, smooth range. Some pairs fall in the middle, close enough to affect each other's shape, but far enough apart to keep their surfaces separate. The universe does not sort things into neat boxes. It spreads them across a spectrum, and every point on that spectrum has its own character, its own appearance, its own quiet drama. What stays the same across all of them is the pull. Every binary pair, no matter how wide or how tight, is held together by gravity. Two stars, born from the same cloud of gas and dust, spending their entire lives in each other's company, circling, glowing, slowly changing each other just by being close. Some binary stars keep a polite distance from each other. They orbit far apart, each one living its own quiet life. But some pairs drift close enough that something stranger begins to happen. One star starts to pull material away from the other, slowly, steadily, like a tide that never stops rising. This process has a name. Scientists call it mass transfer. It happens when one star grows large enough that its outer layers drift into the gravitational grip of its companion. Gravity is patient. It doesn't rush. It simply pulls, and the gas follows. To understand why this happens, you have to think about something called the Roche lobe. That's the invisible boundary around each star in a binary system. The region where that star's gravity is the dominant force. Think of it like a bubble of influence. As long as a star stays inside its own bubble, its gas stays put. But when a star swells and its outer atmosphere pushes past that boundary, the companion's gravity takes over. The gas no longer belongs to the star that made it. Stars swell for a reason. As a star ages and begins to run low on hydrogen fuel at its core, it expands outward into what astronomers call a red giant. A bloated, cooler star many times larger than it once was. Our own sun will do this someday, billions of years from now. In a binary system, that expansion can bring a star right to the edge of its Roch lobe, and then past it. When that happens, the feeding begins. The gas doesn't fall straight across from one star to the other. It spirals. As the material leaves the donor star, it carries angular momentum, that spinning, curving force that keeps planets in orbit and makes figure skaters spin faster when they pull in their arms. That momentum causes the stolen gas to wrap around the receiving star in a wide, flat ring. Scientists call this an accretion disk. It glows. The friction inside the disk heats the gas to extreme temperatures, and it shines with a pale blue-white light, sometimes brighter than either star on its own. Accretion disks are some of the most energetic structures in the known universe. The gas inside them doesn't just glow in visible light. It radiates in ultraviolet light and even X-rays, forms of light that human eyes can't detect, but that telescopes in space can see clearly. When astronomers spot a binary system blazing in X-rays, they know something intense is happening. Material is falling inward. Energy is being released. The system is alive with motion. The star doing the feeding is called the donor. The star receiving the material is called the accretor. These aren't just poetic names. They describe a real, ongoing exchange that can last for millions of years. The donor slowly shrinks as it loses mass. The accretor slowly grows heavier. The balance of the whole system shifts quietly over enormous stretches of time. What the accretor does with all that new material depends entirely on what kind of star it is. If it's a normal, middle-aged star still burning hydrogen, the extra mass just adds to its bulk. It grows a little brighter, a little hotter. But if the accretor is something more exotic, a white dwarf, a neutron star, or a black hole, the results are far more dramatic. Those stories come later. For now, it's enough to sit with the image of two stars locked in this slow, intimate exchange, one giving and one receiving across the silence of space. There's something almost geological about it. The way a river carves a canyon over millions of years, grain by grain. The way glaciers grind mountains down to plains. Mass transfer works on the same patient timescale. The universe doesn't hurry. It doesn't need to. It has all the time there is. And this process isn't rare. Astronomers estimate that a significant portion of close binary systems will experience mass transfer at some point in their lives. It's one of the most common forms of stellar interaction in the galaxy. Two stars, born together from the same cloud of gas, end up changing each other in ways that neither could have managed alone. That's the quiet truth hiding inside binary systems. They aren't just two stars sharing an orbit. They're partners in a long, slow process of transformation. What one star loses, the other gains. The gas that once burned inside one sun ends up glowing in the disk around another. Nothing is wasted. Everything moves somewhere. The universe keeps its own careful accounts. Some stars don't shine at a steady glow. They pulse. They dim and brighten in a rhythm as reliable as the tides. And in binary star systems, this flickering light tells us something remarkable about the hidden order of the cosmos. When two stars orbit each other, they sometimes pass in front of one another from our point of view here on Earth. Each time one star crosses in front of its partner, it blocks some of that partner's light. The total brightness we see drops. Then the crossing star moves on, and the light returns. This happens again and again, in a cycle as steady and predictable as a heartbeat. Astronomers call these systems eclipsing binaries, and they are one of the most useful tools in all of stellar science. The most famous eclipsing binary has a name that sounds almost like a myth. Algol in the constellation Perseus has been watched by humans for thousands of years. Ancient Egyptian astronomers may have recorded its dimming cycle in a calendar more than 3,000 years ago. Every 2 days, 20 hours, and 49 minutes, Algol fades noticeably. Then it brightens again. This cycle never breaks. It never drifts. It repeats with the quiet precision of a clock that has been running since before our civilization began. What makes Algol so striking is how much it dims. At its faintest, it loses about 2/3 of its normal brightness. That's not a subtle flicker. On a clear night, a careful observer can notice the change with nothing more than their own eyes. For ancient skywatchers who had no telescopes and no understanding of what a star actually was, Algol must have seemed deeply strange. Some cultures called it the demon star. They sensed something unusual in it, even if they couldn't explain what. We now know that Algol is actually a 3-star system. 2 of those stars orbit each other closely, and it's their mutual eclipses that cause the dimming we see. The 3rd star orbits much farther out, taking nearly 2 years to complete one loop around the inner pair. The whole system is about 90 light years away, which means the light we see tonight left Algol around the time people were first beginning to explore the Americas. Eclipsing binaries aren't just beautiful to watch. They're scientific tools of extraordinary power, because we can measure exactly how much light is blocked during each eclipse and exactly how long each eclipse lasts. We can calculate the actual sizes of both stars. We can figure out how fast they're moving. We can determine the distance between them. No other type of star system hands us so much information so cleanly. Astronomers describe eclipsing binaries as nature's own measuring sticks. The light curve of an eclipsing binary, which is the graph of how its brightness changes over time, has a very specific shape. It shows 2 dips per orbit. The deeper dip happens when the dimmer, cooler star passes in front of the brighter one. The shallower dip happens when the brighter star passes in front of the cooler one. Each dip has its own depth, its own width, its own slope. Reading that curve carefully, a skilled astronomer can reconstruct the entire geometry of the system, almost like reading a blueprint. Some eclipsing binaries have very short cycles. A pair of stars locked in a tight orbit might eclipse each other every few hours. Others have cycles that stretch across months or even years, because the stars are farther apart and moving more slowly. The length of the cycle tells us directly how wide the orbit is. Kepler's 3rd law, a rule of orbital motion first described by the astronomer Johannes Kepler in the early 1600s connects orbital period to orbital size with beautiful mathematical precision. Binary stars follow this law without exception. There's something deeply calming about a system that works this way. The light dims, the light returns, the cycle repeats. Across hundreds of light years of empty space, these two stars keep their rhythm without fail. They don't need anything to remind them. Gravity holds the pattern. Physics writes the schedule. And here on Earth, we point our instruments at the sky and read that schedule like a page from a book the universe has been writing for billions of years. Every eclipsing binary is a clock. Every flicker is a tick. And the fact that we can hear that ticking from so far away, that we can decode it and understand it and use it to measure the very sizes of distant suns, says something quiet and wonderful about the way this universe is built. It wants to be understood. It leaves the measurements right there in the light, waiting for someone patient enough to look. Some binary stars keep a careful distance from each other. They orbit at a respectful remove, each one burning alone in its own private space. But some pairs pull so close together that something remarkable happens. They touch. These are called contact binaries. In a contact binary, two stars share the same outer layer of gas. That shared layer is called a common envelope, and it wraps around both stars like a single glowing skin. The two stars inside are still distinct objects, still burning with their own nuclear fires. But from the outside, they look like one long, stretched, egg-shaped blob of light. The most studied contact binary in our sky is called W Ursae Majoris. It sits about 160 light years from Earth, which in cosmic terms is practically next door. W Ursae Majoris is so close that its two stars complete a full orbit around each other in less than 8 hours. Think about that. In the time it takes most of us to sleep and wake and have breakfast, those two stars have circled each other completely. Contact binaries like this one are surprisingly common. Scientists estimate that roughly 1 in every 500 sun-like stars in our galaxy is a contact binary. They tend to be smaller, cooler stars, the kind astronomers call K-type and G-type stars. which are orange and yellow stars slightly smaller than our own sun. Hot, massive stars can form contact systems too, but the smaller ones seem to hold together longer. What makes a contact binary so strange is the way energy moves between the two stars. Even though they may have started with different masses, the shared envelope lets heat flow from one star to the other. Over time, the two stars reach nearly the same surface temperature. They balance each other out. A hotter star shares its warmth with a cooler one, and they settle into a kind of thermal truce. Scientists find this deeply puzzling because the two stars are still separate objects with different internal structures. Yet, their surfaces glow at almost identical temperatures. The shared envelope itself is a wild place. It's not a calm, smooth layer of gas. It churns and flows. Magnetic fields from both stars tangle together inside it. Enormous star spots, which are dark, cool patches on a star's surface, similar to sunspots on our own sun, form and shift across the shared surface. The whole system rotates together as one unit, spinning faster than almost any single star of its size would spin alone. That fast spin matters. It's actually what brings contact binaries to their fate. Over millions of years, a contact binary slowly loses energy. The two stars spiral inward, drawn even closer by the forces they generate. Eventually, scientists believe they can no longer stay separate. The two stars merge completely. They become one. This kind of merger is called a stellar coalescence, which simply means two stars blending into a single new star. The result is a fast-spinning, slightly bloated star that looks unusual compared to others its age. Astronomers think they've identified stars in our galaxy that formed this way. These merged stars are sometimes called blue stragglers because they appear younger and hotter than the other stars around them, as if they somehow cheated time. In 2022, astronomers announced they had found a contact binary system called ZTF-J+, 1222, that behaves in a way unlike almost anything seen before. It has a third star orbiting far out around the inner pair, and the whole system completes its outer orbit in just 10,000 years, which is extraordinarily fast for a triple system. The inner contact pair orbits each other in under an hour. It's one of the tightest, most extreme systems ever recorded. What contact binaries remind us is that stars are not isolated points of light. They reach toward each other. They share. They change each other simply by being close. The gravity between two nearby stars doesn't just keep them in orbit. It reshapes them, stretches them, pulls material from one to the other, and eventually, over vast stretches of time, draws them together entirely. There's something quietly moving about that. Two stars born from the same cloud of gas, circling each other for billions of years, growing closer and closer until they finally become one. The universe doesn't always pull things apart. Sometimes it brings them together so completely that the boundary between them disappears. Contact binaries sit at the far edge of what we think of as a binary system. They're the point where two becomes almost one. And in that strange in-between state, they tell us something true about how matter and energy behave when two worlds share everything they have. When one star in a binary pair dies, nothing stays the same. The whole system shifts. The surviving star finds itself in a new universe, one it was never built for. And what happens next can be among the most violent, strange, and beautiful events in all of astronomy. Most stars don't explode when they die. The sun, for example, will one day swell into a red giant, a bloated, cooling star many times its current size, and then slowly shed its outer layers into space. What remains is a white dwarf, a small, dense core about the size of Earth, glowing faintly like an ember in the dark. In a binary system, this process doesn't just affect one star. It reshapes the relationship between two. As a star swells into a red giant, it grows so large that its outer layers can spill across the invisible boundary between the two stars. That boundary is called the Roch lobe, the region where one star's gravity controls the gas around it. When the dying star expands past its own Roch lobe, its material begins to flow toward its companion. The companion star catches that gas. It grows heavier. It spins faster. The dying star, meanwhile, loses mass and shrinks. Two stars, one giving and one taking, locked in a slow exchange that lasts thousands of years. This transfer of mass changes both stars in ways that would never happen if they lived alone. A companion star that gains mass can become hotter and brighter than it ever would have on its own. Scientists have found binary systems where one star appears far too young and energetic for its age. And the reason is that it fed on material from its aging partner. The star didn't cheat time. It borrowed energy from someone else's clock. The record for the most extreme mass transfer in a known binary system belongs to a class of systems called Algol-type binaries, named after the star Algol in the constellation Perseus. Algol sits about 90 light-years from Earth. It contains a bright, massive star and a dimmer, puffier companion. The strange thing is that the dimmer star is actually the older one. In a single star, the more massive star ages faster. But in Algol, the originally heavier star lost so much mass to its companion that it became the smaller one. The companion grew large and bright, while the donor shrank and faded. Astronomers call this the Algol paradox, and it was one of the first clues that binary stars don't follow the same rules as stars living alone. When the dying star finally collapses into a white dwarf, the system enters a new and quieter phase. The white dwarf sits there, dense and cooling, while the surviving companion continues to burn. If the two stars are close enough, the white dwarf's gravity can pull gas from the companion's surface. That gas falls onto the white dwarf and forms a thin, hot layer on its surface. The white dwarf is no longer just cooling. It's collecting. White dwarfs are extraordinarily dense. A single teaspoon of white dwarf material would weigh roughly 5 tons on Earth. They pack the mass of a star into a sphere not much larger than our planet. Their gravity is immense. When gas from a companion star falls onto that surface, it doesn't land gently. It slams down and heats up to millions of degrees. The pressure builds, and sometimes it ignites. That ignition is called a nova. Not a supernova, just a nova. A sudden, brilliant flash as the layer of stolen hydrogen on the white dwarf's surface explodes in a nuclear burst. The white dwarf itself survives. the explosion blasts the outer layer away into space, and the whole cycle can begin again. Some white dwarfs have been caught doing this repeatedly, flaring up every few decades as they collect and burn stolen gas over and over. These are called recurrent novae, and they are among the most reliable explosions in the sky. The most extreme case is a white dwarf that keeps collecting mass until it reaches a critical limit. That limit is called the Chandrasekhar limit, named after the physicist Subrahmanyan Chandrasekhar, who calculated it in 1930. It sits at about 1.4 times the mass of the Sun. If a white dwarf crosses that line, it can no longer support itself. The whole star collapses and explodes in a type Ia supernova, one of the brightest events in the universe, bright enough to outshine an entire galaxy for weeks. Two stars, one dies slowly, one survives, and in that slow exchange, the universe produces some of its most extreme and dazzling events. Some endings are quieter than others. When a star like our Sun reaches the end of its long life, it doesn't explode. It simply lets go. It swells into a red giant, sheds its outer layers like a slow breath, and leaves behind a small, dense core. That core is a white dwarf. It's about the size of Earth, but it holds roughly half the mass of the original star. A single teaspoon of white dwarf material would weigh about 15 tons here on the ground. In a binary system, this process becomes something stranger and more beautiful than it sounds. When one star in a pair ages faster and becomes a white dwarf, the other star is often still living its normal life. The two continue to orbit each other, just as they always have. Nothing dramatic happens right away. The white dwarf glows faintly, a pale blue-white ember against the dark. It no longer fuses hydrogen in its core. It simply radiates the heat it still carries, slowly cooling over billions of years, like a coal pulled from a fire. White dwarfs cool so slowly that scientists believe most of the ones that formed in the early universe are still warm today. The universe simply hasn't been around long enough for them to go fully cold. A completely cold white dwarf, sometimes called a black dwarf, is thought to be purely theoretical at this point. None are believed to exist yet. Now, here is one of those small details that scientists find quietly astonishing. The surface of a white dwarf is extraordinarily smooth. Its gravity is so strong, roughly 100,000 times stronger than Earth's gravity, that any bump or mountain on its surface would collapse almost instantly. The surface is pulled flat. Scientists estimate that the tallest feature on a white dwarf might be only a few centimeters high. A perfectly smooth, glowing sphere drifting silently through space. In a binary pair, the white dwarf's gravity also pulls on its companion. If the two stars orbit closely enough, the white dwarf begins to draw a thin stream of gas away from the living star beside it. This gas doesn't fall straight down. It spirals inward, forming a flat, glowing ring called an accretion disk. The disk shines brightly as the gas heats up from friction. Some accretion disks glow so hot they emit ultraviolet light and even low-level X-rays. All of that light comes not from the stars themselves, but from the space between them. There's something worth pausing on there. The brightest light in that system isn't coming from either star. It's coming from the act of transfer itself, from matter falling through space toward something dense and hungry. Over time, the white dwarf gains mass from this slow feeding. It grows heavier. And this is where the story of a white dwarf pair becomes one of the most precise and important stories in all of astronomy. White dwarfs have a mass limit. Scientists call it the Chandrasekhar limit, named after the physicist Subrahmanyan Chandrasekhar, who calculated it in 1930 when he was just 19 years old. That limit sits at about 1.4 times the mass of our Sun. If a white dwarf gains enough mass to cross that line, it can no longer support itself. Something dramatic follows. But that story belongs to the next section. For now, stay with the quieter picture. Two white dwarfs can also orbit each other directly. This happens when both stars in a binary pair have aged and died, leaving two small, dense embers circling one another in the dark. These double white dwarf systems are surprisingly common. Scientists estimate that a significant portion of binary stars will eventually become double white dwarf pairs. They orbit in silence, cooling so slowly that the the process is almost impossible to measure on a human timescale. Some double white dwarf pairs orbit each other very closely, completing a full orbit in just a few hours. As they do, they release a kind of energy called gravitational waves, tiny ripples in the fabric of space itself. These ripples carry energy away from the system, causing the two stars to slowly spiral closer together over millions of years. It is one of the most patient processes in the universe. Two cooling stars drawing together 1 centimeter at a time across timescales longer than the age of the Earth. There is something deeply calm about that image. Two old stars, long past their burning years, drifting quietly toward each other through the dark, not in any hurry, just following the gentle pull of the universe's rules, the same rules that have guided every star, every orbit, every slow collapse since the beginning of everything. For thousands of years, people looked up and saw a star appear where no star had been before. It burned bright for a few nights or a few weeks. Then it faded slowly back into the dark. They called it a new star. The Latin word for new is nova, and that name stuck. But the star wasn't new at all. It was something far stranger. The ancient Chinese kept careful records of these sudden lights. So did Korean and Japanese astronomers, centuries before European skywatchers paid much attention. These observers wrote down the dates, the brightness, the colors, and how long each new light lasted. They didn't know what caused it, but they watched and they wrote it down, and those records survived. Centuries later, those notes would help modern scientists piece together the truth. In Europe, the idea that the sky never changed held firm for a long time. The stars were thought to be perfect and fixed, set in place forever. When a bright new light appeared in 1572, a young Danish astronomer named Tycho Brahe measured it carefully. He showed it was far beyond the moon, out among the stars themselves. The sky, it turned out, could change. That single observation cracked open a door that never closed again. But what caused these sudden flares? That question took centuries more to answer. By the 1800s, astronomers had better tools. They could split starlight into its colors using a device called a spectroscope. which works the way a prism does, spreading light into a rainbow of information. Each element burns with its own set of colors. By reading those colors, scientists could learn what a star was made of. When they turned their spectroscopes toward a nova, they found something surprising. The light showed signs of fast-moving gas, blasted outward at enormous speed. Something explosive had happened. The real breakthrough came in the early 20th century. Astronomers began to suspect that many novas happened more than once. A star that flared and faded might flare again, years or decades later. These were called recurrent novas, meaning they came back. That pattern was a clue. A one-time explosion might come from many causes, but a repeating explosion pointed to a system, something cycling through the same process over and over. The answer, when it came, was elegant. A nova isn't one star exploding. It's a white dwarf, the small, dense core left behind when a sun-like star dies, stealing gas from a companion star beside it. The white dwarf's gravity is powerful. It pulls hydrogen, the lightest and most common gas in the universe, off the surface of its partner. That stolen gas settles onto the white dwarf in a thin layer. Over time, that layer grows. The pressure at the bottom builds and builds. Then it ignites all at once in a nuclear explosion, a runaway fusion reaction that blasts the stolen gas into space in a brilliant flash of light. The white dwarf itself survives. It's not destroyed. The explosion happens only in that thin outer layer of borrowed fuel. Once the gas is gone, the white dwarf sits quietly again, waiting. Its companion keeps losing gas. The layer builds again, and in time, perhaps in decades, perhaps in thousands of years, it happens again. This understanding came together slowly through the work of many people. The American astronomer Cecilia Payne-Gaposchkin spent years studying novas in the mid-20th century. She analyzed their light curves, the graphs that show how brightness rises and falls over time, and found patterns that helped confirm the binary star model. Her work built on earlier observations and pushed the field forward in ways that are still recognized today. The first nova ever confirmed to repeat was RS Ophiuchi, a system about about 5,000 light years away. It has flared multiple times in recorded history, most recently in 2021, when it briefly became visible to the naked eye. Each time it flares, astronomers watch closely. Each eruption teaches them something new about the timing, the mass transfer, and the physics of that thin, burning layer. What makes this history so striking is how long the answer took to arrive. People watched novas for more than 2,000 years before they understood what they were seeing. The tools had to be invented. The ideas had to be tested. The data had to pile up slowly, observation by observation, across generations of patient skywatchers who never stopped asking what that sudden light could mean. The universe kept its secret for a long time, but it left clues in every flash, in every fading light, in every careful note written by hand under an open sky. And eventually, the clues were enough. Here is something that surprises almost everyone who first hears it. The most powerful explosions in the known universe don't always come from the biggest stars. Sometimes they come from something small, dense, and quietly waiting. A white dwarf is a dead star. It's about the size of Earth, but it carries roughly the mass of our entire sun packed into that tiny space. It's not burning anymore. It's not fusing anything. It just sits there, cooling slowly over billions of years, like an ember that never quite goes out. Most people assume a dead star stays dead. In a binary system, that assumption is wrong. When a white dwarf orbits close enough to a living companion star, it can pull material off that companion. This is called accretion, which simply means the slow, steady gathering of stolen matter. The white dwarf doesn't ask for much at first. It just takes a little hydrogen at a time, letting it settle onto its surface in a thin, growing layer. This is the same process that causes the smaller nova explosions described earlier. But something different can happen if the white dwarf keeps feeding long enough. As more and more mass piles onto the white dwarf, something remarkable begins to build. The white dwarf gets heavier. Slowly, over thousands or even millions of years, it creeps toward a very specific limit. Scientists call this the Chandrasekhar limit, named after the physicist Subrahmanyan Chandrasekhar, who calculated it in 1930. That limit sits at about 1.4 times the mass of our Sun. A white dwarf cannot hold itself together beyond that point. The pressure from its own weight becomes too great for its structure to resist. What happens next is extraordinary. The entire white dwarf, all of it at once, ignites in a runaway nuclear explosion. This is not a surface flash like a nova. This is the complete destruction of the star itself. The explosion is called a type Ia supernova, and it releases more energy in a few seconds than our Sun will produce in its entire 10 billion year life. The white dwarf doesn't just explode. It ceases to exist. Nothing is left behind. Here is the part that scientists find genuinely strange. Because every type Ia supernova happens at almost exactly the same mass. They all produce almost exactly the same amount of light. Every single one. This makes them extraordinarily useful. Astronomers can look at a type Ia supernova in a distant galaxy, measure how bright it appears from Earth, and calculate almost precisely how far away that galaxy is. A standard candle is what scientists call any object with a known true brightness. And type Ia supernovae are among the most reliable standard candles in all of astronomy. This is where the story takes a turn that even surprised the scientists who discovered it. In the late 1990s, two independent teams of astronomers were using type Ia supernovae to map the expansion of the universe. They expected to find that the universe was slowing down. Gravity, after all, should be pulling everything back together. What they found instead was the opposite. The distant supernovae were fainter than expected. The universe wasn't slowing down. It was speeding up. Something was pushing everything apart, faster and faster. Scientists named this unknown force dark energy, and it remains one of the deepest unsolved mysteries in all of physics. The discovery came directly from studying binary star explosions. There's another counterintuitive detail worth sitting with. The companion star in a type Ia supernova system survives. The white dwarf vanishes completely, but the star it was feeding from gets blasted by the shockwave and flung outward at tremendous speed. Astronomers have actually found these runaway stars, moving through the galaxy at velocities that make no sense unless something catastrophic happened nearby. They carry the memory of the explosion in their motion. They are stars that witnessed the death of their partner and were thrown clear. The universe recycles everything. The iron and calcium and silicon scattered by a type Ia supernova don't disappear. They drift outward into the surrounding gas clouds, seeding the next generation of stars and planets. The calcium in your bones was forged in stellar explosions. Some of it may have come from a white dwarf that once quietly orbited another star, stealing just enough mass over millions of years to finally tip past that invisible line. A dead star, a living companion, a slow theft, and then the brightest light for billions of miles in every direction. It's a sequence that seems impossible until you understand how gravity and time work together. And it all begins with two stars quietly circling each other in the dark. When a massive star dies, it doesn't simply vanish. It collapses. The core crushes inward with such force that protons and electrons are squeezed together into neutrons. What remains is a neutron star, a dense, spinning ball of matter, roughly the size of a city, but heavier than the sun. And sometimes that neutron star is not alone. Many massive stars live their whole lives in binary pairs. When one of them finally explodes in a supernova, the explosion is violent enough to tear some binary systems apart. The two stars go their separate ways, flung into the galaxy like stones from a sling. But sometimes the system survives. The gravity between the two stars holds on. The neutron star stays in orbit with its companion, and something remarkable begins. The companion star is still alive. It's still burning. And the neutron star, with its crushing gravity, begins to pull material away from it. Streams of gas spiral inward, falling toward the neutron star in a slow, glowing whirlpool. That whirlpool is called an accretion disk, a flat ring of heated gas that glows brilliantly as it spirals down. The temperatures inside that disk can reach tens of millions of degrees. The gas shines in X-rays, a kind of light far too energetic for human eyes to see. This is where the connections begin to show themselves. A star that died billions of miles away is now feeding on its partner. The death of one thing becomes the engine of something new. The neutron star, born from destruction, is now gathering energy again, slowly, patiently, over millions of years. As the neutron star pulls in more and more material, something changes. It begins to spin faster. Angular momentum, the same force that makes a spinning skater speed up when she pulls in her arms, causes the neutron star to accelerate as mass falls onto it. Over millions of years, it spins faster and faster. Some neutron stars in binary systems end up rotating hundreds of times every single second. Scientists call these millisecond pulsars. They are among the most precise natural clocks in the known universe. The pulses they send out, tight beams of radio waves sweeping through space like a lighthouse beam, arrive at Earth with extraordinary regularity. Astronomers can measure the arrival of those pulses down to tiny fractions of a second. And because the neutron star is in orbit with a companion, those pulses shift ever so slightly as the star moves toward us and then away. That tiny shift tells scientists the mass of both stars, the size of the orbit, and even lets them test Einstein's theory of general relativity. The idea that massive objects bend and warp the space around them. One of the most famous examples is a system called the Hallstaler binary, discovered in 1974. It contains two neutron stars orbiting each other. Scientists watched this pair for years and noticed something extraordinary. The orbit was slowly shrinking. The two stars were spiraling closer together, losing energy in the form of gravitational waves, ripples in the fabric of space itself. Einstein had predicted these waves decades earlier. The Hallstaler binary was the first indirect proof that they were real. Russell Hulse and Joseph Taylor won the Nobel Prize in Physics for that discovery in 1993. This is what makes binary neutron star systems so much more than a curiosity. They are laboratories. They let scientists test the deepest laws of physics in conditions that no experiment on Earth could ever recreate. The extreme gravity, the precise timing, the slow orbital decay, all of it becomes data. All of it becomes understanding. And the connections reach further still. When two neutron stars finally spiral close enough, they collide. The collision is called a kilonova, a blast of light and energy that briefly outshines entire galaxies. In 2017, scientists detected both gravitational waves and light from a kilonova for the very first time. What they found inside that explosion was gold and platinum and uranium, heavy elements that cannot be made inside a normal star. They are forged only in the violence of colliding neutron stars and scattered across space to eventually become part of new planets, new oceans, new living things. The gold in a ring on someone's finger was made in a moment like that. Two neutron stars, once part of two separate binary systems, spiraling together over billions of years, finally meeting in a flash of light that seeded the galaxy with the rarest elements in existence. Every system feeds the next. Every death carries something forward. The neutron stars in their quiet orbits are not isolated. They are part of everything. Some stars end their lives quietly. They cool and fade over billions of years, leaving behind a small, dense cinder. But some stars die violently. They collapse inward with such force that not even light can escape. What remains is a black hole, a region of space where gravity has become so strong that nothing, not even light, can pull free. And sometimes that black hole is not alone. When a massive star collapses into a black hole, its companion star is still there, still burning, still orbiting. The two were born together from the same cloud of gas, and now one has become something almost impossible to imagine. The other continues its slow, steady life, unaware of what its partner has become. The orbit continues. The dance goes on. This is where things begin to change. A black hole on its own is invisible. It gives off no light. It makes no sound. If it floats alone in space, far from any other matter, we would never know it was there. But a black hole with a companion star is a different thing entirely. The companion star sheds material from its outer layers, the way a candle loses wax as it burns. And if the black hole is close enough, its gravity pulls that material in. The material does not fall straight down. It spirals. It forms a wide, flat disk around the black hole, the way water spirals slowly down a drain. Scientists call this an accretion disk, a spinning ring of gas and dust that circles the black hole before falling in. As the gas spirals inward, it moves faster and faster. It heats up. It glows. A black hole that was invisible moments ago now blazes with fierce, hot light. This is one of the great slow changes in the life of a binary system. The companion star, over millions of years, loses mass. The black hole gains it. The balance between them shifts, little by little, across timescales longer than the entire history of life on Earth. The black hole grows. Not quickly, this is a patient process. But over time, the companion star shrinks. Its outer layers are drawn away, pulled into that spinning disk, and then beyond. Scientists believe that in some systems, the companion star can be stripped down to almost nothing. What began as two roughly equal stars becomes something very different. A black hole and a tiny, exhausted remnant, still orbiting each other in the dark. The orbit itself changes too. As mass transfers from one object to the other, the gravitational balance between them shifts. The two objects move closer together or drift apart, depending on how the mass moves. In some systems, the orbit tightens over millions of years. The companion star spirals slowly inward, drawn toward the black hole by the same gravity that has been stealing its outer layers. This is a transformation measured not in years or centuries, but in deep geological time. And yet, even as the companion star shrinks, it continues to feed the disk. The disk continues to glow. The system continues to change, slowly and steadily, like a river carving a canyon. There is something worth sitting with here. A black hole is often described as a destroyer, and in one sense, that is true. It pulls matter in and does not give it back. But in a binary system, that same process powers some of the brightest objects in the galaxy. The energy released by infalling gas is enormous. It radiates outward in X-rays, in ultraviolet light, in forms of energy that our eyes cannot see, but our instruments can detect across across thousands of light years. The black hole does not just consume, it transforms. Evidence suggests that some black holes in binary systems have been actively pulling material from their companions for millions of years. The companion star, slowly giving up its mass, is being changed by the relationship. So is the black hole. So is the orbit. Nothing in this system stays the same. Everything is in motion. Everything is shifting. Everything is connected to everything else. The universe does not rush. These changes happen on timescales that make human history look like a single breath. But they are happening right now in systems scattered across our galaxy. Somewhere out there, a black hole is pulling gas from a companion star. The disk is spinning. The light is blazing. The orbit is slowly, quietly tightening. Two objects bound together by gravity, changing each other across millions of years. One invisible, one burning. Both locked in a slow, patient transformation that will not end for a very long time. Some of the brightest objects in the entire sky cannot be seen with human eyes at all. They shine not in visible light, but in X-rays, a form of light so energetic that our atmosphere blocks it completely. To see these objects, scientists had to send telescopes into space. And what those telescopes found was staggering. When a neutron star or a black hole orbits a normal companion star, something remarkable begins to happen. The powerful gravity of the compact object, that dense, collapsed remnant, pulls gas away from its partner. That stolen gas doesn't fall straight in. It spirals downward in a wide, flat disk, the way water circles a drain. Scientists call this an accretion disk. And as the gas spirals inward, it moves faster and faster, packing tighter and tighter until friction heats it to temperatures of millions of degrees. At those temperatures, the gas stops glowing in ordinary light. It glows in X-rays. The result is one of the most violent and luminous events the universe produces on a regular basis. These systems are called X-ray binaries. A single X-ray binary can radiate more energy every second than our sun releases in an entire year. Some of the brightest X-ray sources in the sky are systems like these. Two stars locked in orbit, one of them quietly feeding the other's hunger. The colors we associate with these systems are invisible to us, but the data tells a vivid story. The inner edge of the accretion disk, closest to the neutron star or black hole, glows the hottest. If we could somehow see it, it would blaze in brilliant blue-white light. Farther out, the disk cools. The gas shifts from white to yellow to deep red at the outer edges. It's a gradient of heat, a slow fade from the unbearable to the merely extreme. Some X-ray binaries pulse. The neutron star at their center spins rapidly, and its magnetic field, a field far stronger than anything on Earth, funnels the infalling gas down onto two small regions near its poles. As the star spins, those two bright spots sweep across the sky like the beam of a lighthouse. We detect a regular pulse of X-rays, arriving with clockwork precision. These are called X-ray pulsars. The pulse rate tells scientists exactly how fast the neutron star is spinning and how that spin is changing over time. Other X-ray binaries burst. In these systems, gas builds up on the surface of the neutron star over hours or days. The pressure and heat grow until the gas ignites in a runaway nuclear reaction. A sudden, brilliant flash of X-ray light that fades over the course of minutes. Scientists call these type X-ray bursts. They happen again and again, cycling through the same pattern of buildup and release, like a slow heartbeat measured in fire. There are also X-ray binaries, where the compact object is a black hole rather than a neutron star. These systems are harder to study because the black hole has no solid surface for gas to land on. Instead, the gas spirals inward until it crosses the event horizon, the point of no return, and vanishes. But just before it disappears, it releases an enormous flood of X-ray light. Some of this energy also escapes as powerful jets, narrow beams of hot plasma that shoot outward from the poles of the disk at nearly the speed of light. These jets can stretch for thousands of light years. One of the most famous X-ray binaries in our galaxy is called Cygnus X1. It sits roughly 7,000 light years away in the constellation Cygnus. Its compact object is a black hole, about 21 times the mass of our Sun. Its companion is a massive blue supergiant star, blazing hot and bright, slowly losing its outer layers to its dark partner. Cygnus X1 was one of the first strong candidates for a black hole ever identified. Scientists debated its nature for years before the evidence became undeniable. What X-ray binaries reveal is that light carries information no other signal can. The timing of pulses tells us about spin. The spectrum of the X-rays tells us about temperature and composition. The way the brightness changes over time tells us about the size and shape of the disk. Every flicker, every burst, every steady glow is a message written in a language of energy. These systems are not quiet. They are the loudest, most radiant objects in the galaxy that still follow the rules of orbital mechanics. Two stars bound by gravity, locked in a dance that produces light so fierce it can only be seen from space. And yet, even here, in all this violence, there is order. There is pattern. There is a kind of fierce, burning harmony. Some stars spin, not slowly, the way a planet turns through its long, quiet day, but fast, impossibly fast, hundreds of times every single second. These are millisecond pulsars. A pulsar is a neutron star, the dense, city-sized remnant left behind when a massive star collapses and dies. Most pulsars spin a few times per second when they're young, but millisecond pulsars spin between 100 and 700 times per second. They are the fastest rotating solid objects we know of in the entire universe. And binary star systems are the reason they exist at all. Here is how it happens. A neutron star sits in orbit with a companion star. Over millions of years, the companion grows and expands. Its outer layers spill across the gap between them. That stolen gas doesn't fall straight down onto the neutron star. It spirals inward, the way water circles a drain. That spiral carries spin with it. It transfers rotation to the neutron star, the way a hand pressed against a spinning top makes it go faster. Astronomers call this process recycling. The neutron star gets spun up faster and faster until it reaches those staggering speeds. Without a companion, this never happens. A A lone neutron star simply slows down over time, like a top losing momentum on a table. It's the partnership that creates the speed. Now imagine what that spinning produces. A pulsar sweeps two beams of radio waves across space as it rotates, the way a lighthouse sweeps its beam across dark water. Each time that beam crosses Earth, our radio telescopes catch a pulse, a click, a beat. For a millisecond pulsar spinning 700 times per second, those pulses arrive 700 times every second. Scientists have converted these radio pulses into audio. The result is a low, rapid hum, a deep mechanical drone, almost like a turbine heard from far away. Some millisecond pulsars, when slowed down and shifted into the range human ears can detect, sound like a steady, low throb. Others sound like a soft, rhythmic buzz. Each one has its own frequency, its own voice. The timing of those pulses is extraordinary. Millisecond pulsars are among the most precise natural clocks in the known universe. Their pulses arrive with a regularity that rivals atomic clocks. The most accurate timekeeping devices humans have ever built. Scientists use arrays of millisecond pulsars spread across the sky as a kind of cosmic timing grid. If a gravitational wave, a ripple in the fabric of space itself, passes through our part of the galaxy, it stretches and compresses the distances between us and those pulsars. The pulses arrive just slightly early or just slightly late. By watching dozens of pulsars at once, astronomers can detect those tiny shifts. The pulsars become a detector, a vast, galaxy-spanning instrument listening for the deepest vibrations in space. This technique is called pulsar timing, and it works because binary stars created these fast, stable, precise objects in the first place. The companion star that spun up the pulsar doesn't always survive the process. In many millisecond pulsar systems, the companion has been almost entirely consumed. The pulsar's intense radiation and particle winds slowly erode the companion star, stripping away its outer layers over billions of years. What remains is sometimes just a tiny, dense remnant, a brown dwarf, or a star reduced to a fraction of its original mass. Astronomers call these systems black widow pulsars, named after the spider that consumes its mate. The pulsar feeds on its partner, takes what it needs, and then slowly destroys what's left. There is something quietly striking about that. The companion gave the pulsar its speed, its precision, its long life as a stable, spinning clock. And in return, the pulsar spent billions of years wearing the companion down to almost nothing. The two objects shaped each other completely. Neither would be what it is without the other. One of the best-known millisecond pulsars, called PSR J4 374715, sits about 510 light-years from Earth. It spins about 174 times per second. It has a white dwarf companion. Scientists have studied it for decades because its pulses are so clean and so regular. It has become one of the anchor points in pulsar timing arrays around the world. When you listen to the converted audio of a millisecond pulsar, there's something almost hypnotic about it. That low, steady hum, that patient, repeating beat. A dead star, spinning in the dark, keeping time with a precision that took billions of years and a partner star to create. The universe, it turns out, makes its own clocks. And it makes them out of catastrophe and gravity and the slow, steady pull of two stars sharing the same sky. There is something quietly wonderful about the way the universe follows rules. Not rigid, cold rules, but deep, simple patterns that repeat at every scale. Binary stars show us those patterns clearly. And one of the most beautiful places to look is in the orbits of planets caught inside these double star systems. Most planets in binary systems fall into one of two broad types. The first type orbits just one of the two stars, staying close enough that the second star feels like a distant sun in the sky. Scientists call these S-type orbits, where the S stands for satellite. The planet hugs one star tightly, and the other star is simply a bright neighbor. The second type is called a P-type orbit, or circumbinary orbit. Here, the planet swings around both stars at once, looping in a wide path that keeps both suns inside its orbit. These are the planets that truly have two suns rising in the morning. Whether a planet can survive in either type of orbit depends on something called the stability zone. Think of it like a safe lane on a road. Too close to the second star in an S-type orbit, and the gravity of that star will tug the planet off course over time. Too close to the two stars in a P-type orbit, and the combined pull of both suns will shake the planet loose. But inside the stable zone, a planet can circle for billions of years without being disturbed. Astronomers have worked out the math on this carefully. For a circumbinary planet to stay in a stable orbit, it generally needs to be at least 3 to 4 times farther from the two stars than the stars are from each other. So if two stars orbit each other at a distance of 1 astronomical unit, roughly the distance from Earth to our Sun, then a circumbinary planet needs to be at least 3 to 4 astronomical units out to stay safe. The numbers are clean and predictable. The universe, it turns out, is a very precise engineer. One of the most famous examples of a circumbinary planet is Kepler 16b. The Kepler Space Telescope found it in 2011. It orbits two stars at once, a larger orange star and a smaller red star, and it sits just inside the outer edge of the stable zone. It's roughly the size of Saturn. From its surface, if it had a surface you could stand on, you would watch two suns set at the same time. The sky would dim in 2 stages as each star dropped below the horizon. What makes Kepler 16 be even more striking is how it was found. When the planet passed in front of one star, then the other, it blocked a tiny fraction of their light. The Kepler telescope measured those dips in brightness with extraordinary precision. Scientists could calculate the planet's size, its orbital period, and the distance between the two stars, all from the pattern of fading light. The math told the whole story. That method, watching for the dip in starlight as a planet crosses in front of its star, is called the transit method. It works because light follows predictable rules. The amount of dimming tells you the planet's size relative to the star. The timing of each transit tells you the orbital period. And once you know the orbital period, Kepler's third law of planetary motion lets you calculate the distance between the planet and its star. One elegant equation connects time, distance, and mass true across the entire galaxy. Johannes Kepler worked out those laws in the early 1600s, long before anyone knew binary stars existed. He was studying the planets in our own solar system. But the rules he found are universal. They apply to a planet orbiting a single star, a planet orbiting two stars, and even two stars orbiting each other. The same simple relationship between orbital period and distance appears everywhere. It's the same quiet logic running through all of it. There's something deeply calming about that. The universe doesn't make exceptions. A planet 300 light years away follows the same rules as the moon above your head right now. The numbers don't change based on where you are. Gravity works the same way in every corner of space, pulling masses toward each other with a force that falls off in a perfectly predictable way as distance grows. Binary stars gave astronomers some of the clearest early measurements of stellar mass, because two stars in orbit around each other are essentially a natural physics experiment. The way they move tells you how heavy they are. The timing tells you the distance. Everything connects. The universe keeps offering the same answer in different forms, patient and precise, waiting for us to notice. Binary stars gave us something that single stars simply cannot. They gave us a way to weigh the stars themselves. When two stars orbit each other, their gravity pulls back and forth between them. That pull follows rules, precise, mathematical rules that never bend. By watching how fast two stars circle each other and how wide that circle is, astronomers can calculate exactly how massive each star must be. No guesswork, no estimates, real numbers pulled straight from the motion of light across the sky. Before binary stars, we had no reliable way to measure a star's mass directly. We could guess based on brightness. We could compare one star to another. But binary systems gave us a scale, a true cosmic scale, where the orbits themselves do the measuring. Every binary pair we study adds one more confirmed data point to our understanding of how stars work. And what we found was delicate, remarkably so. A star's mass controls almost everything about it. Mass decides how hot a star burns. It decides what color the star glows. It decides how long the star lives and how it dies. A star just a little more massive than our sun will burn hotter, live shorter, and end more violently. A star just a little less massive will burn cooler, glow red, and last for hundreds of billions of years. The difference between those two fates can come down to a fraction of the sun's mass. Binary stars showed us exactly where those lines fall. They gave us real examples, side by side, of stars at different masses living out their lives together. We could watch one star age faster than the other. We could see one swell into a red giant, while its partner still burned quietly on the main sequence. That long, stable phase of a star's life where it fuses hydrogen in its core. Seeing both stages at once in the same system taught us things we could never have learned from a single star alone. There is something quietly astonishing about this. The universe handed us a laboratory. Two stars bound together, each one a different chapter of the same story. All we had to do was watch. Mass also controls something even more fragile: the habitable zone. That narrow band of distance around a star where temperatures allow liquid water to exist on a planet's surface. Move a planet slightly closer to its star, and the oceans boil away. Move it slightly farther, and they freeze solid. The width of that zone depends almost entirely on the star's mass and the heat that mass produces. Our sun sits at a mass that creates a habitable zone wide enough for Earth to exist comfortably within it. Not at the edge, not barely inside, comfortably with room to breathe. Scientists believe this is not a coincidence of position alone. It reflects a precise balance between the sun's mass, Earth's distance, and the thin layer of atmosphere that wraps our planet like a second skin. That atmosphere is thinner than most people imagine. If Earth were the size of a basketball, the atmosphere would be thinner than a single coat of paint. And yet that thin coat holds in just enough warmth. It filters out just enough radiation. It keeps the oceans liquid and the air breathable. Change the sun's mass by even 10%, and the habitable zone shifts. Earth might fall outside it entirely. Binary star systems showed us how rare this balance is. In a close binary, where two stars orbit within a few million miles of each other, the combined heat and shifting gravity make stable planetary orbits nearly impossible in the inner system. Any planet trying to hold a steady path would be tugged first one way, then another, pulled between two competing suns, until its orbit stretched into something wild and unpredictable. The conditions for liquid water, for steady seasons, for a calm and lasting climate would be very hard to maintain. Wider binary pairs are gentler. A planet orbiting far outside both stars in what scientists call a circumbinary orbit can sometimes find stability. But the window is narrow. The mass of each star, the distance between them, the shape of their shared orbit, all of it has to line up just right. What binary stars taught us, more than anything else, is that stability is earned. It is not the default state of the universe. Chaos is the default. Gravity pulls in every direction. Stars flare and swell and die. Orbits shift over millions of years. The fact that anything holds together long enough for life to take root is, when you look at it clearly, one of the most remarkable things in all of space science. Not every question about binary stars has an answer. Some of the deepest mysteries in astronomy live right here, in the space between two orbiting suns. Scientists have studied these paired systems for centuries, and still, the universe keeps a few secrets close. One of the biggest open questions is surprisingly simple to ask. How exactly do wide binary stars stay together? Wide binaries are pairs of stars separated by enormous distances, sometimes more than a light year apart. A light year is about 6 trillion miles. At that distance, the gravity holding them together is incredibly weak, almost too weak to explain. And yet, these pairs exist. They orbit each other slowly over millions of years. Scientists are still working out how they survive so long without drifting away into the dark. Part of the mystery is what happens when the galaxy itself nudges them. The Milky Way is full of moving objects, giant clouds of gas, clusters of stars, the slow churn of the galactic disk. These forces pass through space like invisible tides. For a tight binary, those nudges don't matter much. But for a wide binary, a single close encounter with a passing star or a dense cloud could be enough to break the pair apart forever. Scientists call this process disruption. What they don't fully understand is how often it happens, and why so many wide pairs survive it anyway. There's another puzzle hiding in the numbers. When astronomers map wide binaries across the sky, they sometimes find more of them than their models predict. The math says many of these pairs should have broken apart long ago, but they haven't. Some researchers think this might hint at something subtle about the structure of gravity itself at very large scales. Others think there are simply more wide binaries forming than we realize, constantly replacing the ones that drift away. Neither answer is settled. The question is still open, and it's a genuinely exciting one. Then there's the mystery of how binary stars affect the planets around them. Scientists have found planets orbiting binary systems, worlds with two suns rising and setting in their skies. But the conditions that allow a planet to form in a binary system are tricky to pin down. Too close to both stars, and the gravity tears the forming disk apart before a planet can grow. Too far, and the planet might not get enough warmth to hold liquid water. The exact boundaries of where a stable, life-friendly planet could exist around a binary system are still being mapped. Every new discovery shifts the picture a little. One of the stranger unsolved questions involves something called the mass ratio. That's the comparison between how heavy one star is versus the other. In many binary systems, the two stars are surprisingly close in mass. They're not identical, but they're often within a factor of 2 of each other. Scientists expected to see more pairs where one star is much heavier than the other. The fact that so many binaries seem to prefer a near-equal match is something the current models of star formation don't fully explain. It might be telling us something important about how stars are born together, something we haven't quite figured out yet. There's also the question of what happens to binary systems in the very oldest parts of the galaxy. The oldest stars formed more than 13 billion years ago in the early universe, when the raw material of space was mostly hydrogen and helium. Binary systems from that era would have evolved very differently from the ones we see today. Some of those ancient pairs may have already gone through every stage, from birth to white dwarf to possible merger, long before our sun even existed. Studying these ancient systems is incredibly difficult. They're faint, they're far, and the signals they send are easy to miss. But finding them could teach us how the very first stars lived and died together. What makes all of this so quietly wonderful is that the gaps in our knowledge aren't signs of failure. They're signs of how rich and strange the universe truly is. Every time a new telescope opens its eye on the sky, binary stars give up a little more of what they've been holding back. The Gaia Space Telescope, launched by the European Space Agency, has already mapped millions of binary candidates across the Milky Way. Future observatories will go further still. The stars that drift apart are not just a mystery to solve. They're an invitation. They remind us that the sky is not a finished painting. It's still being made. And somewhere out there, two stars are slowly pulling away from each other, and we are just beginning to understand why. Some binary systems are so well studied, so carefully watched over so many years, that they've become landmarks in the sky. They're the ones astronomers return to again and again. Each one tells a different part of the story of how two stars can live together, change each other, and eventually become something new. Albireo is one of the most beautiful of these. It sits at the head of Cygnus, the Swan constellation, and through even a small telescope, it shows two stars side by side. One glows a deep amber gold. The other burns a cool, steady blue. The contrast is striking, warm and cool light sitting close together in the dark. Scientists debate whether these two stars are truly bound by gravity or simply appear close from our angle of view. But even if they're only an optical pair, they've introduced more people to the night sky than almost any other object. That golden and blue glow has a way of stopping people cold. Sirius, the brightest star in our night sky, is also a binary. Most people don't know that. The brilliant white star we see is called Sirius A, and it has a small, dense companion called Sirius B. Sirius B is a white dwarf, the cooling remnant of a star that already lived and died. It's roughly the size of Earth, but carries nearly the mass of our sun. Sirius B was the first white dwarf ever confirmed by astronomers back in the 1860s. Its discovery helped scientists understand that stars don't simply vanish when they die. They leave something behind. Sirius B orbits its bright companion once every 50 years, tracing a slow ellipse through space while Sirius ablazes on. Then there is Algol, sometimes called the demon star. Ancient astronomers noticed that it dimmed and brightened on a regular schedule, though they didn't know why. We know now. Algol is an eclipsing binary, two stars orbiting each other so that one passes in front of the other from our point of view. Every 2.87 days, the dimmer star crosses in front of the brighter one, and Algol fades noticeably in the sky. It then brightens again as the eclipse ends. This cycle has been running for longer than human civilization has existed. Algol also has a third companion star orbiting the inner pair at a much greater distance, making it a triple system. The demon star is busier than it looks. Beta Lyrae is another system that has taught astronomers a great deal. It's a contact binary, two stars so close together that they share an outer envelope of gas. One star is pulling mass from the other right now, steadily, over thousands of years. The receiving star is growing. The giving star is shrinking. In perhaps 100,000 years, the smaller star may be consumed entirely, leaving only one star behind. Beta Lyrae is a system caught in the middle of its own transformation. Watching it is like watching something become something else in slow motion. Eta Carinae is one of the most extreme binary systems in our galaxy. It contains two massive stars, and the larger one is among the most luminous objects known. It shines with the energy of 5 million suns. In 1843, it briefly became the second brightest star in the night sky, outshone only by Sirius, before fading back below naked eye visibility. That eruption released more energy than most stars emit in their entire lives. Scientists believe the larger star in Eta Carinae is close to the end of its life. When it finally explodes as a supernova, the event will be visible from Earth, even in daylight. The smaller companion star orbits the larger one in a long, looping ellipse, swinging close every 5.5 years before pulling away again. Each of these systems, Albiro's colored light, Sirius, and its quiet ghost, Algol's steady dimming, Beta Lyrae's slow consumption, Eta Carinae's violent brilliance, represents a different chapter in the life of a binary pair. Some are young and stable. Some are aging and changing. Some are on the edge of something enormous. The universe doesn't hold still. Every system is moving through time toward a different shape of itself. Far from now, Eta Carinae's larger star will end in fire and light. Sirius B will cool further, fading from white to yellow, to red to black over billions of years. Beta Lyrae will merge into one, and somewhere in the galaxy, the gas and dust left behind by all of these endings will drift together, cool, and begin to form something new. Stars that end become the seeds of stars that haven't started yet. The sky is always in the middle of becoming. Step back now. Let your eyes go soft and wide. Imagine you are floating somewhere far above the Milky Way, looking down at the whole galaxy spread out below you like a slow, glowing wheel. From up here, the stars are countless. There are somewhere between 200 billion and 400 billion of them in our galaxy alone. And here is something quiet and remarkable. Roughly half of all the stars you can see from Earth are not single stars at all. They are pairs. Two stars bound together, circling one another in the dark. Some estimates suggest that among the oldest, most massive stars, the fraction of binaries climbs even higher. Perhaps 70 or 80% of them were born with a companion. That means the night sky is not a field of lonely lights. It is, in large part, a sky full of partners. Look toward the center of the galaxy. The stars there are packed more tightly together than they are out here in our quiet corner of the Milky Way. In those dense, crowded regions, binary systems form and interact at a faster rate. Stars pass close to one another. Gravity tugs at existing pairs. Some binaries are broken apart by a passing neighbor. Others are formed when two unrelated stars drift close enough to capture each other. The galaxy's center is a place of constant, slow reshaping. Out here in the spiral arms, the long, curving streams of stars that sweep outward from the galactic core. things are quieter. Our own sun sits in one of these arms, roughly halfway between the center and the outer edge of the galaxy. The sun has no stellar companion. It travels alone, but most of its neighbors do not. Nearby binary systems like Alpha Centauri, just 4 light-years away, remind us that paired stars are the normal state of things. We are the exception, not the rule. Across the galaxy, binary stars have been quietly shaping the chemical story of the universe for billions of years. When a massive binary system ends in a supernova, that enormous stellar explosion, it scatters elements into the surrounding gas clouds. Iron, calcium, oxygen, carbon. These atoms drift outward and eventually mix into the clouds that will collapse to form new stars and new planets. Some of the iron in your blood was forged in a star that exploded long before our sun was born. Some of it may have come from a binary system where one star's death triggered the others. The calcium in your bones almost certainly came from supernovae. So did the oxygen you breathe. Binary systems, with their higher rates of certain kinds of stellar explosions, contributed to that supply. The universe built you slowly across billions of years, using the wreckage of dead stars. That is not a small thing. Scientists have found binary stars in every kind of environment the galaxy offers. They exist in globular clusters, those ancient, tightly packed balls of hundreds of thousands of stars that orbit the outer edges of the Milky Way. They exist in open clusters, the younger, looser groups of stars that formed together from the same gas cloud. They exist in the thin, scattered regions between the spiral arms, where stars are few and far apart. Wherever stars form, binaries seem to follow. Even in other galaxies, binary systems appear to behave the same way. The physics does not change. Gravity is gravity. The same forces that pull 2 stars into orbit around each other here work the same way in the Andromeda galaxy, 2.5 million light-years away. The same way in the faint, distant galaxies that appear as tiny smudges in the deepest telescope images. The universe runs on consistent rules, and binary stars are one of its most common expressions of those rules. There is something deeply calming about that. The universe is vast beyond imagining. Distances between galaxies are so large that the numbers lose all meaning. And yet, the same gentle gravitational pull that keeps the moon circling the Earth also keeps one star circling another across the entire observable universe. The same force, the same quiet, patient math. Every binary system out, there is a small, private world of its own. Two stars, sometimes close enough to share their outer layers, sometimes so far apart that a single orbit takes millions of years, each one following the same invisible thread of gravity, each one part of the larger turning of the galaxy, which is itself part of the larger turning of the universe. The galaxy is full of pairs. The universe is full of connections, and you are part of all of it, made from the same ancient atoms, resting quietly under the same stars. We have come a long way tonight. We started with the simple, stunning idea that most stars in the sky do not travel alone. More than half of all the stars we can see have a companion. Two suns bound together, pulling on each other across distances we can barely imagine. And from that one quiet fact, an entire universe opened up. Binary stars are not just a curiosity. They are one of the most useful tools astronomers have ever found. Because when two stars orbit each other, their gravity tells us things. It tells us how massive they are. It tells us how far apart they sit. It tells us how fast they move. A single star, alone in the dark, keeps most of its secrets. But a paired star gives itself away. The math of their dance reveals the truth. That is how we learned to measure the mass of stars in the first place. Without binary systems, we would have had to guess. Instead, we watched two stars circle each other, and we listened to what the numbers said. Every mass measurement we have for stars today traces back, in some way, to what binary systems taught us. And the story goes deeper than measurement. Binary stars shaped the universe we live in. When one star in a pair grows old and swells into a red giant, it can spill material onto its companion. That companion grows heavier. It changes. Sometimes it explodes. The explosion scatters iron, carbon, calcium, and oxygen across thousands of light years of space. Those elements drift for millions of years. gravity pulls them together again. New stars form, new planets form, and on some of those planets, perhaps, something stirs. The calcium in your bones was forged in a stellar furnace. Some of it may have passed through a binary system before it ever reached this solar system. The iron in your blood may have traveled through the heart of an exploding white dwarf. You are not separate from these distant, ancient fires. You are made of them. That is the quiet truth that runs beneath everything we have talked about tonight. The universe is not a collection of separate things. It is one long, slow process, passing matter and energy from one form to the next. Stars are born. Stars age. Stars die. And what they leave behind becomes something new. Binary stars are one of the great engines of that process. They accelerate it. They amplify it. They make the universe more creative than it would be if every star simply burned alone. Even the strangest objects we discussed tonight fit into this picture. Neutron stars spinning hundreds of times per second, spun up by a companion that fed them mass across millions of years. Black holes pulling streams of glowing gas from a partner star, blazing with X-ray light, so bright they outshine entire galaxies. Millisecond pulsars ticking like the most precise clocks in existence, their rhythm a gift from a star that no longer exists. Every one of these objects carries the memory of a relationship. Every one of them was shaped by something else. Nothing in the universe becomes what it is entirely on its own. Right now, somewhere in the Milky Way, two stars are circling each other in the dark. They have been doing this for billions of years. They will keep doing it for billions more. They do not rush. They do not falter. They simply move, steady and slow, in the quiet of space, held together by nothing more than gravity and time. And right now, somewhere much closer, you are lying still. Your breathing has slowed. The world outside is dark and quiet. The same gravity that holds those two distant stars together also holds you gently to this planet. The same atoms that burned inside ancient stars are resting now inside you. You are part of the same long story. You always have been. The galaxy is turning slowly overhead. Its 100 billion stars are moving, each one on its own long path, most of them paired with a companion they will never leave. The universe is vast, and it is old, and it is full of fire and silence in equal measure. But tonight, from where you are, it is simply quiet. The stars are out, the dark is soft, and everything from the farthest binary pair to the breath in your chest is exactly where it belongs. Rest now. You have seen something true tonight. The universe is enormous, and it is gentle, and you are held inside it. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet dreams.